Hi everyone, and welcome to this video on the p-value and significance level. So in this video what we're going to do is we're going to go through an example from one of the previous weekly activities to try to show you the idea of the p-value and significance level working together. And so this starts off with a question. What is the chance that I am wrong in my analysis? So remember, we're never saying anything in this class 100%. And the reason for that, you're about to see. The reason for that is because no matter what we do, even if we follow the statistical process perfectly, we could still be wrong in our conclusion. And so the significance level gives us a way to try to understand that idea, and the p-value gives us a way to connect our statistic back to that. Okay, so it all comes down to this idea. What's the chance I'm about to mess this up? So, back in week 3, what did I have us do? Go back and check your weekly activity. What did I have us do? I had you guys flipping coins. So you did flips of, you did 10 flips, 15 flips, 20 flips, and recorded that for me. So what I have here are the results of 46 samples. So in this case, remember, this 46 samples here, right here, this is each person. So 46 students, each of you went and you flipped a coin 20 times. And then what you did was you told me what proportion of heads you got. That's each dot here. Each dot here is the proportion of heads out of 20 coin flips. So remember, each of these is a p-hat that each of you got. You each flipped your coin and you got this. Okay. So if I was then to bring in the new stuff, if I was then to say, okay, now what I want you to do is do a hypothesis test. I want you to test to see if your coin is fair. Okay, so right here, you should be getting 50-50 heads, 50% heads, about, that's what we think, right? If it's a fair coin. If it's not a fair coin, you should be getting something different in the long run. So we went over this in week 6. We made these together. So I'm just bringing that in now, bringing it all in. Well, okay, from that point, you would say, I'm sitting here with my 1p hat that I actually have from flipping my fair coin. This is what should happen, and so I run a simulation. So here's my simulation I ran. I told the computer, hey computer, flip a fair coin, do it 20 times like I did, and then I want you to replicate that. I want you to actually do those 20 flips 1,000 total times. The picture is here that we get, our nice little bell curve. And then I took the extra step, which you would do as well, up to this point, of doing the 2SD method to figure out what statistics would be usual and unusual for a fair coin. So you should redo this calculation to practice this, but if you do this calculation with the two numbers I have here, you'll get that on the low end, 0.275, I drew that here, that's my little blue cutoff here, and on the high end, 0.719, about 72% here. So, stop for a second, remind ourselves what this means. If you come up and you say, here's my coin, I flip it 20 times. If you get a percentage of heads in this blue box, what do we say? We say, okay, it's plausible you have a fair coin. I'm all done. If you come up to me, you flip your coin 20 times, and you get a percentage of heads that's outside the blue box here in this pink region, then we say, ooh, that's unusual. I'm going to reject that it's a fair coin. So this is up through 2.1. This is all stuff that we've covered. We're still practicing, of course, but we've covered. Okay, so then what? Then you as the student would compare your statistic to this. You'd say, my 20 flips, am I in the blue box, am I not? Okay. So here's just a reminder. What happened with the 46 students and their samples? So this is 46 different students. Each one of you is a dot, and you would each go to this picture Usual, unusual, usual, unusual. Each of you would go to this picture and try to figure it out. Now let's look at what happens here. So take a little bit of time to do this on your own. But if you go through and you look at these numbers, we're going to end up with 2 students right here. 1, 2. 2 students who are going to look at the picture. They're going to say, look at me, I'm a student. This is what I got. And they're going to go to the picture and go, oh, I'm unusual. Or not I'm unusual, maybe, but my throws of my coin, my flips are unusual. So 2 students are going to look at this and go, oh, okay, unusual. And then everybody else, the other 44 students, and again, you should double check this, that these numbers are working out, right? That each of these dots is in the blue box over here, are going to look over here and say, oh, okay, usual. So we have to pretend for a moment we are all actually flipping fair coins, which is, I think, a fair, no pun intended, assumption, right? So we're all flipping fair coins, but look what happened. Even though we were all flipping fair coins, you'd expect, what do you expect? You expect if you're flipping a fair coin, you're going to be in the blue box. But not everyone was. And so we have to think about this. I did everything right. I flipped a fair coin. I did the simulation. I set up my hypotheses. I did it all right. And you're telling me that there's still a chance that I could do this all right, flip my fair coin, and get something unusual. Yeah. It's random. There's randomness. We're never sure about anything, 100%. It's still possible that you could do everything right, flip your actual fair coin, and get something unusual. That's what happened to 2 students. Look at these 2. So, okay, well, how does this have anything to do with what we've talked about? Well, it's a lot to do, but specifically, 2 out of the 46 students got unusual samples flipping a real fair coin. Okay? 2 out of 46, plug that into your calculator, is this number, 0.044. This looks very familiar. It almost looks like 5%. Wait a minute, 5%. Where have I seen 5% before? Our usual, unusual picture. Remember, 95% of samples are the usual. 5% of samples are the combined unusual. Right? So we already knew that this should happen. This picture is not telling you if you have a fair coin and flip it 20 times, you will be in the blue box. No, it's saying that 95% of all samples should be in this blue box, and 5% of students who do this should actually, even with a fair coin, end up outside the box. We expect that. I could have guessed, without having seen any of this, that between 2 and 3 students would have gotten unusual by just quickly doing a calculation of 5%. I expect 5% of the 46 students to get something unusual. We should expect this. That is the point of this 5% rule, 95%. That's our setup. We are expecting 5% of students to be having unusual results here. Okay, so I know that's weird. It's like we're setting ourselves up for failure. But that's the point of this significance level idea, is that we know there's a chance we can mess this up. And what do I mean by mess it up? Well, so let's actually do that. Like what I keep saying mess it up. What do I mean mess it up? Let's pretend we're one of these students that got an unusual statistic, okay? So we're going to run it through here. So I'm picking out, I'm this student. So here is me. This is not actually me, but it's a dot, but that's fine. So this is me. I'm student who got 20% heads on my 20 flips. So I say, okay, I go to the applet. I make the simulation, same one as above. I then can use the applet to calculate this thing called the p-value. The p-value, if we go up, the p-value, there's a definition in the book. It says the probability of getting a sample statistic like the one observed or more extreme if the null hypothesis is true. Is this, right? So what's going on here? Okay, so what's happening here? In terms of the significance level, we can replace this definition with this question. What's the chance I'm about to mess this up right now? So the p-value is telling us this is the chance you're about to mess this up right now. So let's go back down to our student. Our p-value is right here, big and red here, 0.01. That's 1%. So the p-value is telling you, student, you got 20% heads. There's a 1% chance if you really have a fair coin. This is important. There's a 1% chance if you have a fair coin for real that you could get something this extreme or more extreme. Wow, 1%. That's small. But guess what? It actually happened. So this student used a fair coin, got this actual 20%, and is about to mess everything up. And that's okay. That's expected for it to happen to someone. This person, whoever you are watching this video, you are actually a person who got this 20% heads. You were the unlucky one in this case. There's only a 1% chance this should have happened to you, and you fell into it. It happens. So what does the student do? The student takes this information and says, okay, well, either using the p-value or my 2SD rule, says, okay, this is an unusual statistic, all right? This is an unusual statistic, therefore, I'm going to reject the null and say, haha, my coin's not fair. Wrong. That's wrong. You have a fair coin. This is the wrong conclusion to make. You did the statistics right. Everything we just said, everything we just did was good statistics. Perfect. But your conclusion's still wrong, because that can happen. The key point here is that the p-value tells us what's the probability that, if you could still keep using the word chance as you say it, right? What's the probability, the chance that you're gonna be wrong based on this assumption you're about to make? And that, in this case, is 1%. And the way we use the p-value and the significance level is this, right here. We say, if my p-value, so my p-value in this case, my percent chance of messing this up, if that's less than alpha, which in this case is 1% less than 5%, I say, I can deal with that. Reject. So I say to myself, okay, I got a 1% chance of being wrong here, but my alpha is 5%, and by making alpha 5%, I'm saying I'm okay with a 5% chance of messing this up. That's what alpha is. Alpha, we go all the way back up to the beginning. What is the chance that I'm going to mess this up? I'm doing this wrong. That's alpha. Alpha is you saying, so let's put this down here. Alpha, when you pick alpha, which we'll be doing in this class, we'll be picking something, is you saying, what percentage chance am I okay with? So I should add to this. What percent chance of being wrong am I okay with? Now we have to be a little more specific here, because this doesn't just give us the percentage chance you're just wrong about any conclusion you make. Specifically, this is the percentage chance you're wrong if you reject. So if I go to reject the null, like I'm doing right now, this is the percentage chance when you set up the problem that you are going to be wrong. So as soon as you set up alpha's 5%, you are saying to begin the problem, you set this up. You're saying, I am okay if I reject this null. If I end up rejecting the null, I'm okay with a 5% chance of being wrong here. That's what alpha is. You're setting yourself up a limit on how wrong you might be when you go to reject the null. If you end up doing that. But if you end up rejecting the null, you're saying, okay, I got a 5% chance of being wrong here using alpha. So if I calculate my p-value and I'm less than that, I'm saying, okay, well, I set up 5% at the start. I'm okay as long as I'm within that range of wrongness. My p-value is 1%. That's less, so I'm in my range. All right, I'm going to reject. I know I could be wrong here, but my percentage chance of being wrong by rejecting the null is less than my allowed cutoff. And so now, hopefully you can see why I might want to change alpha, depending on the situation. There may be situations where a 5% chance of incorrectly rejecting the null is too big. You might sit there and write that and say, no, I can't live with that. The consequences of rejecting the null might be too big for 5%. I might need to change that. I might need to change the cutoff, maybe 1%, maybe even smaller than that. So that's something we're going to have to think about. You're going to have to think about. And is different in different fields. So 5% is generally our kind of go-to cutoff. But that's something you have to think about. What are the consequences of each decision I could make and being wrong about each decision? There's only 2 decisions you can make. Null is plausible, reject the null. And so you need to think to yourself, if I'm wrong with either of these, what's the consequences? And then from that answer, you can start thinking about what alpha should be. So let's just see what would happen and connect all these dots now with a usual statistic. So I'm going to go up here and we'll pick out one person, this one. This person here. This is a new p-hat that I'm going to use, 0.6. So I go down here, 0.6. Go to the applet, we plug it in, put 0.6 in. It shades in all the samples that were as extreme as 0.6 or more extreme. So I see 0.6 and everything to the right, and then it just hops over the middle to 0.4. So I hop over to 0.4 and everything there, because this is two-sided. Okay, so my p-value is 0.514. Right? Using just the regular definition, that says there's a 51.4% probability or chance of getting my statistic, 0.6 or 60% heads, or more extreme, assuming a fair coin. That's high. That's a pretty good chance. That's better than a coin flip. Ha ha ha. So that's better than a coin flip. That's better than 50-50 that something this extreme could happen to you. So how do you know how to use this p-value then, right? How to use this? Well, your p-value, in this case, my p-value is greater than my cutoff by a lot. If my p-value is greater than my cutoff, I am happy to say null is plausible. I say, okay, cool. This is a fairly likely scenario to have happened using a fair coin, so I'm good. Null is plausible. How we can just quickly do this is you just take your p-value, you compare it to alpha. If your p-value is bigger, null is plausible. Just that's it. Boom. P-value bigger, null plausible. P-value smaller, reject the null. Okay. So the one thing I'll say here is this action of us saying the null is plausible, this also has a corresponding percentage chance you mess this up. It's just much more complicated than being able to pick out alpha. So we're not really going to talk about that in this class. But just to remind you that there's two conclusions you can make. Null is plausible, reject the null. The two options. Alpha gives you the probability of being wrong when you reject the null. So alpha and reject the null are connected. The null is plausible is a separate conclusion you can make, and the probability of that happening different than alpha. So something a little more complicated. But that's it. That's p-value and alpha. Alpha, again, just to remind you, what's the percent chance of being wrong when I reject the null? That I'm cool with. Like, yep, okay, I'm fine with a 5% chance of messing this up. You can change that, but that's what we'll start with. Your p-value tells you, using my sample, what's the percent chance of having my statistic or more extreme happen. If that's less than my cutoff, I'm feeling pretty good. Let's reject. If the p-value is bigger than this cutoff, I'm saying, you know what? Too big. Let's just go null is plausible. I'm not confident enough right now to reject any null. The probability of getting something as extreme as mine, too big. All right? There's too big of a chance that I'm messing this up if I reject the null. So, white flag, null is plausible. I'm good. And there you go. P-value, significance level. Okay, it's all about this question. What's the chance I'm wrong? But specifically, I just want to make sure now that we've talked about it, it's a specific wrong. So, what's the chance I'm wrong when rejecting the null? So, now that we've got to dig into it a little bit more, we should add this caveat. What's the chance that I'm messing this up if I reject the null right now? That is the big question that connects them. So check this out, think this over. We'll talk about this in class. But the nuts and bolts that you really have to get down from this right now are just how you make your conclusion. Take your p-value, compare to alpha. There's two options. P-value less than alpha, reject. P-value bigger than alpha, null plausible. Done. So right now, make sure you can just get that piece down, and then you can think more and more about this connection between alpha, the p-value, and how this all plays together. All right, make sure you're asking me questions, come in office hours, if you have anything about this.